Andy Lee, Science Geek.
Hello, today we will be doing a fluid balance experiment on a frog using adenosine, ADH, and histamine. To begin, we have to dissect the frog. To dissect the frog, we must open him up, take out all the guts, leaving the heart, lungs, and kidneys in place. Once the heart is fully exposed, we must make a cut in one of the branches of the aorta and insert the catheter. Once this is complete, we will take our frog, heart, catheter, intact, and we will hang it from the weight transducer. Once this is complete, we can fill our funnel with our solution of choice, and we are now ready to begin our experiment.
Hey, stupid.
What's your name?
I just got the results of my dancing experiment, and explain it to me.
Let's see, what were they?
So the drip rate increased by 7 drips per minute,
Okay.
and the weight increased by 0.05050505 grams per minute.
That's good data. Alright, sit down and I'll explain it to you. To explain drip rate, we need to understand Ohm's law. Professor Equation will come up and explain Ohm's law for you.
Ohm's law.
What's Ohm's law?
Hold on. Ohm's law is Q equals change in P over R.
What's Q?
Q is the flow rate through the vessels.
What's P?
P is pressure.
What's triangle?
Triangle stands for delta, which means change in something, which in this case is change in pressure.
What's R?
R is resistance.
What's resistance?
Resistance is, well, let me show you. Do you get it? Okay, you don't get it. It's 8 times eta times L divided by pi times R to the 4th.
What's eta?
Eta stands for viscosity.
What's L?
L stands for length.
What's pi?
Something you need. Okay.
What's R?
R is the radius of a vessel.
That's nice.
So, when you have an increase in drip rate, that means your Q is increasing, which means
What's Q?
Q is flow rate through the vessels.
So higher
like I said
drip rate
earlier.
means higher flow through the vessel?
Yes, correct.
Oh.
You're correct. Okay, so it means either change your P or our resistance changes. But obviously, change in P is not the change in P because we didn't mess around with the funnel, which would have changed the pressure in the vessels. Instead, so it has to be a change in R, resistance. Would it be a change in the viscosity? No, because we didn't change the solids in it. Would it be a change in length? Nope, because the vessels don't change their length, unless it's by magic. Is it a change in pi? No, because that's a constant.
What if I ate it?
It still wouldn't change. And would it be a change in R? Yes, that would be the only thing left. If you don't get anything, well, perhaps Professor will explain it to you.
So what? We're working with adenosine on vascular smooth muscle cells, correct? On vascular smooth muscle cells, there are two types of adenosine receptors, A1 and A2. A1 is coupled with GI, A2 is coupled with GF. A1 causes vasoconstriction, A2 causes vasodilation. So, adding adenosine comes and binds. We know that there are more GS or A2 receptors because it causes vasodilation, right? So,
Experimentally?
Yes. So, adenosine comes and binds. This activates adenylate cyclase, which ATP converts ATP into cyclic AMP. Okay. Cyclic AMP then comes and activates PKA. PKA phosphorylates myosin light chain kinase and myosin light chain phosphatase. Okay. PKA has a negative effect on myosin light chain kinase, which allows myosin to be phosphorylated, and has a positive effect on myosin light chain phosphatase, which makes myosin dephosphorylated. Okay. So when myosin is not phosphorylated, it is inactive. Since there is a positive effect on myosin light chain phosphatase, it causes more inactive myosin, which causes relaxation, which is vasodilation.
Well, that's only half of it.
The weight change, exactly. Well, to look at weight change, we need to look at Starling's law, and we'll have Professor Equation come up and explain Starling's equation for you.
So, Starling's equation. Starling's equation is V, which is flow filtrate through the capillaries, equals the K.
What's the difference between V and Q?
This is flow through the capillaries into tissues, which is, while Q, on the other hand, is flow through the lymph cells. Get it? Okay, so K is the permeability coefficient, and then you got times the pressure in the capillaries, or pressure of the capillaries, as the oncotic pressure of the interstitial fluid, subtracted by the pressure of the interstitial fluid plus the oncotic pressure of the capillaries. And that is Starling's equation.
That's nice.
So, our results show an increase in weight. So how does that happen? So, you know that vasodilates, right? From Professor's explanation. And when you have an increase in or when you have vasodilation in arterioles, it causes an increased flow to the capillaries, which then increases the pressure in the capillaries. When you increase pressure in the capillaries, it will increase P, which will thus give you an increase in weight. And that is our discussion probably for adenosine.
Oh, I get it.
Bye.
Hey, Smarty Pants.
Hi.
So I got the other part of my other experiment, and you need to explain this to me too.
Okay, what was the other part of your experiment?
ADH.
Okay, and what were your results? Let's see.
So, drip rate increased by 3 drops per minute, and weight increased by 0.0493 grams per minute.
Alright, sit down and I'll explain it to you. One thing to notice is that your trends were the same as adenosine, right? They both increased. Correct. So, as Professor Equation explained before with Ohm's law and Starling's equation, do you think anything in here changed?
No.
No, exactly. Is that correct, Professor Equation?
What don't you get?
I get it.
Okay.
Thanks, sir.
Alright, so you're wondering, well, what's different then, right? Okay. Well, with ADH, they have different receptors, okay? So, on vascular smooth muscle membrane or in cells, we have V1 coupled with GQ, and V2 receptors coupled with GF. Just different names, right? We remember we had A1 and A2 before. So V1 causes vasoconstriction, V2 causes vasodilation. Alright, same mechanism as before with adenosine. ADH comes in, binds, activates adenylate cyclase, which converts ATP to cyclic AMP, which activates PKA, which phosphorylates NLPK, which is myosin light chain kinase, and MLCP, which is myosin light chain phos. It causes relaxation, which causes vasodilation, which increases drip rate and increases weight.
And we get vasodilation because there's more V2 than V1?
Exactly. They're just like adenosine, there was more A2 than A1. There's more V2 than V1 in ADH. Got it?
What about weight change?
So the weight change, remember, that deals with Starling's equation, correct? Right, so since we had vasodilation, we had of the arterial, right? Remember? Whoops! Don't be a smart aleck. Since we have vasodilation of the arterial, we have more flow, right? We have more fluid flowing through, which causes the increase in pressure, which allows more fluid to flow into the tissues. Basically, more or less.
Hey, you.
Sorry.
I got the results for the rest of my experiment. You need to explain it to me.
What experiment?
Histamine.
Oh, okay. What are your results?
The histamine decreased the drip rate by 7 drips per minute, and histamine decreased the weight by 0.0162 grams per minute.
Oh, why don't you ask Professor Equation?
Okay. So,
So from his explanation, the decrease in radius is equal to vasoconstriction, and histamine has 2 receptors, histamine 1 and histamine 2. Histamine 1 is coupled to the GQ protein, and histamine 2 is coupled to GS protein. Since our result is based on constriction, so we will only talk about the GQ pathway. The histamine binds to H1 receptors and then activates phospholipase A, which splits PIP2 into DHG and IP3. IP3 activates the IP3 receptor on the sarcoplasmic reticulum, which lets calcium out. And DHG also activates protein kinase C, which inhibits potassium channels and activates L-type calcium channels, which allows calcium to come into the cytosol. Calcium binds to calmodulin, which activates MLCK, myosin light chain kinase, that phosphorylates myosin and causes contraction, which is why blood vessels vasoconstrict.
What does K plus channels do?
Potassium channels basically repolarizes, so PKC inhibits potassium channels to prevent potassium from flowing out of the cytosol.
So the cell can't repolarize?
Yeah.
Oh, so it stays depolarized and then it stays contracted?
Yes.
Oh. So what about weight?
Weight, we'll go back to Professor equation. That will explain this.
So as you can see, the weight decreases. What does that do to Starling's equation? Which would decrease your weight.
Oh. Oh.
Where are you going?
So, basically from this experiment, we found out that the frog that we did our experiment on had more B2 receptors, more A2 receptors, and more H1 receptors based on the changes in flow rate and weight that we observed in the frog. Yeah, that concludes our experiment with ADH, adenosine, and histamine. Thanks for watching!
Sweet.
Annie Lee Science.